Now we'll talk about the packing fraction of hexagonal closed packing system. That we are talking about the packing fraction. What is the hexagonal closed packing system? It is like this, 2 hexagon at the top and bottom, and of course this is like this, is like this. So you can understand that over here atomic distributions are like this, it is like this, all the atoms are like this, atoms are like this, and you know, at the half of the height, let's say height is c, and at the half of the height c by 2, we get another equivalent octal hexagonal face in which 3 atoms are like this. So therefore we can say that this is like this, and also at the face centers also the atoms are there in the opposite faces. So therefore this is the hexagonal closed pack system. We can say hexagonal closed pack system. By the name you understand it's a closed pack system, hexagonal closed pack system, where you know that we know A equal to B, not equal to C, and also alpha equal to beta is equal to 90 degree, and gamma is not equal to, gamma is equal to basically 120 degree. Over here you can look over here, x, y, z axis if you take. Now we have to calculate the packing fraction. Just look at all corners atoms are basically can be shared by, you know, this is basically is 1 hexagon, you can see this 1 hexagon, this 1 hexagon. So therefore this atom can be shared by this plane and this plane and this plane from the top and from the bottom. So therefore the shear is 1/6 each one. Face center is always half, and this is full 1 1 1. So therefore if we calculate the corner atoms 1/6 into total is 12 into 12 plus, you can say 1 2 3 4 5 6 6 6 12, and 2 into half, you can say plus, it is your inside is 3 completely inside. So therefore we can get is the total number of total effective number of atoms, and also you can call it rank, effective number, total effective number of atoms, or we can call rank basically, or we can call rank, and that value coming out to be 6. Now of course the packing fraction how we can calculate is nothing but 6 into each unit, each atom has got volume 4/3 pi r cube, that divided by, we can say volume of the whole this crystalline structure, and this length is A, this length is A, we know. So it is a basically, I can think of this is basically mixture of, I mean you can think of that this hexagonal plane is consisting of 6 equilateral triangles. Let's say O, let's say A, it is a O, it is a B. 6 AOB types of triangles are there. So therefore we can write how many 6 faces, 6 triangles are the equilateral, 6 into √3/4 a square, because we know the area of a equilateral triangle is √3/4 a square into basically it is a C is basically the height of the unit cell. So we understand that packing fraction is the 6 times of the, since 6 is the rank of the HCP lattice, so 6 times of the volume of the units, volume of the one sphere or the one atom, and divided by the volume of the total hexagonal crystalline system. So therefore 6 into √3/4 a square into C, because each length is A, we know, A into C, where C is basically the height of this particular prismatic crystal. So therefore this C we don't know, but A we know, A equal to 2, or how? Because they are in contact, these two atoms are in contact. So I can write A basically equal to 2R. So A equal to 2R, equation 2, it is, let's say, equation 1. Now we have to calculate what is C, basically what is C in terms of R, because you know in the packing fraction we can't have any R, A, etc. So now look at over here. Over here you can see the green atoms are like this, green atoms at the half of the height C/2, this is basically C/2, it is basically this plane, I'm talking about this, and the top atom is just sitting over here like this. Now just look at, if I take the all centers like this over here, we can get this kind of structure, this and this. So they are in the plane, and I am drawing a perpendicular to this, which is basically meeting at void. Now obviously this we can connect this and I can draw the perpendicular over here, so therefore it will be 30 degree because they all make 60 degree to each other. So now what you get is that these are in connectivity, so it is 2r, of course it is 2r, it is c by 2, this height is c by 2, so of course with the help of Pythagoras theorem is 90, so we can find out what is this. Now just look at over here, if I say O, A and B, of course AB is equal to basically R, AB equal to R. So what is OA? OA equal to R sec 30, we can see from the trigonometry, sec 30 is equal, cos 30 is equal to base by hypotenuse, so sec 30 is the hypotenuse by base, so base will be equal to hypotenuse, cos theta is equal to base by hypotenuse, so sec theta is equal to hypotenuse by base. So obviously we can say in terms of base, this hypotenuse OA equal to R sec 30 because we know AB equal to R, so therefore this is R sec 30. So we can write OA square plus OC, let's say it is OD square is equal to basically AD square. So with the help of this, we'll be able to find out the relation between R and C. How? OA is equal to, OA equal to R square sec square 30 plus degree plus, we can say OD square is equal to C square by 4, and of course we'll be getting AD square, it is basically your 4R square. So we can write C is equal to 4R by 4 root 3, 4R by root 3. We can calculate this one. This is basically R square sec square 30. Over here R square sec square 30, it is R square into sec cos 30 is equal to root 3 by 2, so it is 4 by 3 basically, and plus C square by 4, that gives you basically 4R square. So therefore we can get R equal to 4, C equal to 4R by root 3. Of course you can say R square 4 by 3 minus 4R square, or 4R square minus 4R square, 12R square minus 4R square, 8R square by 3, so it is 32R square by 3, so it is 4 root 2 by root 3R, 4 root 2 by root 3 into R. So this is basically we get from C. So that means what is C? We can replace the C equal to also 4 root 2 by root 3 into R. That is basically C. We have got from third equation. From here this calculation is very important to us, and A equal to 2R like this. So with the help of this A, 2R and this C, if we put C over here, if we put A over here, then we get the values approximately 0.76 as we found in the packing fraction of the face-centered cubic lattice. So therefore face-centered cubic lattice and hexagonal close packed system is basically similar kind of packing fraction. Just I will show you that how the difference of the layers takes place in the three-dimensional diagram. You will look at after my lecture, and we'll discuss the voids and limiting radius ratio, and with some standard type of crystals, that is crystalline and the ionic as well as the covalent crystals. So with this I will conclude now for the packing fraction. Next you will see some diagrams of the three-dimensional diagrams of the unit cells, and also the types of voids, types of packings like that. It will come in the next slide. Today we will be discussing the voids. Today we will be discussing voids and pattern of arrangement of atoms. Arrangement of atoms in FCC, that is also called cubic closed packed system, and HCP system. Why we talk about this? Because these are coming under the category of closed packing, and it can be non-closed packing. That is, for that examples are basically the simple cubic or primitive cubic, or you can say cubic primitive. So there are two basically systems. One is non-closed packing. So packing can be two types. One can be closed packing, another can be non-closed packing. In the closed packing we get basically FCC and HCP, And in the non-closed packing we get cubic system. For example, how cubic system is developed is that one atom is like this, another atom is like this, like this. So this is, you can say, the base, and then after that again if you put another layer like this, and like this, it gives rise to a cubic system like this. That is primitive cubic. We can say that one atom is above this, another atom is like this, we can say like this,